Welcome to our NPTEL courses on the power quality improvement technique. Today we are going to discuss about this will be a second lecture on the multipulse converter, and thereafter we shall discuss about the 3-phase PWM rectifier. So, first let us take out the multipulse converter. As we have seen in our previous class, that is a 12 pulse converter, and that is quite easy, there you require to have a just one star and delta transformer, and this will be star and there will be a delta, and there will be a phase shift of 30 degree, and you have seen that this will ensure cancellations of the 5th and the 7th harmonic. It is because of that fact that 5th harmonic, if you see that it is the 5th harmonic and the 7th harmonic, and if they have been phase shifted fundamental by 30 degree and they become exact phase opposition in case of the star and delta, and thus they cancel each other, and in that way 5th and 7th harmonics are been eliminated. So, when you gave a phase shift or minus 20 degree and plus 20 degree, so what happened, you got a 20 degree phase shift. So, what happened then, and it is a 12 pulse 18 pulse converter. So, you divide it by 360 degree, essentially you are going to get, instead of the 12 you are going to get 11, and thus this primary current I A in the start site will be I A prime, that is the 20 degree phase lead, and that is a star star connections, but it requires a special kind of construction that we require to do it. So, it gives you delta equal to 0, and this one it will give delta equal to minus 20 degree, and we shall see that even it can cancel the harmonic 11 and 13. So, for this reason what happen, if you can superimpose these 3 waveforms, ultimately it leads to the fundamental one. First of all, blue one is a I A prime. So, that is essentially I A by 3, and thereafter you got this one as I A, and thereafter you got I A. So, this particular waveform, maybe blue one, has the THD of 23% if it is fully loaded, and once you add this all these waveforms, so then what happened, till 5th, 7th, 11th, 13 are been eliminated, and since they are eliminated, you are left with the next harmonic, that is 18, that in 18 pulse will be 17th and the 19th. So, lowest harmonic after fundamental will be the 17th harmonic, and thus you can expect the full load THD to be less than around 3%, and that is quite, it is within all these standard proposed, because generally all those want that THD to be less than 3%, and you can close to the 3% in case of the full loading. So, ultimately this will looks like the current profile in the start site. So, this is the waveform which we can see that this is the IA, this is a 6 steps waveform. They are phase shifted by 20 degree, this is minus 20. Thereafter this one is at 0, we assume that there is 0 phase shifted. So, this will be the case, and next will be plus 20 degree. So, you can add them together, and ultimately you can find that the THD what you were ultimately it will, you will construct in a primary side, the reflected current will be the IA, this will have this kind of ripple, and ultimately if you see that this this waveform. This one is fundamental and this one is your, this is a real waveform from the experiments. This is the its fifth harmonic, this is the seventh harmonic, this is 11th and the 13th harmonic, thereafter this one is 17th and the 19th harmonic. So, if you and if you take the harmonic spectrum of it, so and current is in the scale of the √2 per unit per division because of the peak value. So, and this one is the, as you can see that it is a 5 millisecond divisions in the your oscilloscope or power scope. So, you can see that here only first harmonic, thereafter this one is 17 and this one is 19. So, all are absent and you can get the desired power quality. But what is the disadvantage of having it? You require a special kind of construction. I am coming to it, to the problem of the multipulse converter, then only we shall start to the PWM converter. So, as you know that, then again the same analysis what we have done for the 12 pulse converter, we are going to repeat it. So, this is something that it is Ls equal to 0.05 and that is 5% or 5% of the in terms of the per unit 0.05, and leakage reactance is considered to be 5%. As you can see that this is the THD in light load, THD will be high, and so for the this one is corresponds to the 0 source inductance. Higher source inductance gives you better THD, but problem will be your lower power factor. So, you can see that you can get less than 2% for C having a 10% generally source impedance does not occurs, but you can get 2%, but considering that 5% source inductance and you can reach well below 3% in the full load condition and thus satisfy your purpose. Same way, this is a curve with the power factor for Ls equal to for Ls equal to 000, that means there is no source inductance, but physically impossible, then you can get this A which will give you a good power factor, but power factor you can see that it is quite good, but THD while high, but thereafter if you increase the source inductance, then you can also get close to 0.97 as power factor, because till 0.95 we do not penalize the customer or the utility does not penalizes the customer, and generally we do not have a source inductance in of 10%, but if you have then you get around 0.95 and that is also quite acceptable. And if you have a 0.95 power factor and THC below 2%, it accepts all the standard. Same way we can extend our discussion to the 24 pulse converter, and the lowest harmonic will be, you can eliminate the 11th and the 5th, 7th, 11th, 13th, 17th, 19th. So, next will be 23 and 25. So, 23 or 25 also will not be present, because your 5th harmonic is absent. You will get even 27th will not be present, because your 3rd harmonic is absent. Ultimately, you get the 29th harmonic. So, 23 and 29, these are two elementary number. So, these two harmonics will be present in the system. Now, in this case, since it is a 24 pulse converter, you will have 4 such converter connected in series, and ultimately you get a huge DC bus voltage, and that may be required for, and you can feed it to the multi-level inverter, and that is a quite requirement for the high power applications, and thus you can, this kind of topology fits well. You see there is one part of it, this part and this part is nothing but your 12 pulse converter. So, you can have a star with respect to it, you can have a 0 phase shift, and thereafter with respect to it you can have a 30-degree phase shift. So, there is a vector group that will operate, it is YD11. So, and same way then this will have a special kind of construction, because you generally have star and delta connections, that is not a challenging. But when you made a 18 pulse converter, that require that itself is a design how you actually go for it, and so this design is little complex, and for this reason we require to have having a 18-degree phase shift or having a 15-degree phase shift. So, we require to have a special kind of transformer to be designed. So, for this reason, but you can have some extent of manufacturing advantage, because you will be using star star and star delta, and this vector group is available to you commercially, but these only two special vector group which you require to make in case of the 24 pulse converter. But whereas if you go back to the 18 pulse converter, you require to make these two special transformer which gives you the 20-degree phase shift. Thus, sometime though it require more component count, from the manufacturing point of view, we do prefer the 24 pulse converter, because it eliminates all the harmonics for the fundamental up to 23rd, and the manufacturing is easy, because you require to manufacture the special transformer of 15-degree phase shift and plus and minus 15-degree phase shift, and there in case of the 18 pulse converter 20-degree phase shift. These are the special transformer you require to make, but both of the cases you require two special transformer. So, these two transformers, these three transformer are readily available to you, and for this reason this has more popularity over the 18 transformer, because see, if the costs of the manufacturing this component become same than the 18 transformer, of course, we may not go for the 18 transformer, because ultimately you get all those entities better. So, ultimately you have all the current, 4 current in this IA, IA delta, IA bar and IA caret will form the primary current IA capital. So, this is the IA delta bar, and that has to be the IA by 4, and this will have a THD of 23 or 24%. Similarly, this is the IA prime, and this is the IA prime bar A. Ultimately, this will have all this 4 current, this has been splitted, upper 2 current is shown here and lower 2 current is been shown here. So, if you add up all those 4 current and you get a THD well below 2%. This is actually this is satisfied all the conditions of your power quality, and that's what happen. You do not have a problem of little underloading. So, you can see at we generally does not have a 0 source impedance, and we having considering that class A is a ideal case generally, class B considering that 5% per unit, and this will have a droop like this, and the THD is around less than 2%, and if you have a little more source inductance, then also you will get THD for below 2%, maybe 1%. And even in a light load, 50% light load, you can see that. Consider this is a typical middleman in the road B, that is 5% source inductance and half load. You can see till that this is a curve B, and it is actually it is crossing the this point 2% THD. So, up below at half of the load, this 24 pulse converter for 5% source inductance, that is quite feasible and practicality into consideration, and with 5% leakage reactance you can get easily 2% THD. Similarly, you can see that your power factor also been improved. So, you have A, B, C, these three curve, and you can see that A gives you generally little less than 98% without any source inductance. Generally, we are interested about B. B is well above 95% in the full loading, and if your loading is decreases, then definitely power factor get better. So, now you have no problem, and C can reach around 93.93, but generally C craft does not have, because it has required huge source inductance and it is generally not externally connected. And for this reason B curve you can take, and B curve you can see that it is matching all the limit when we were discussing the limiting condition for the THD and power factor, it can consider all the limits. Now, till now we have seen the series operation of the converter. So, series operation of the converter, and that get reflected ultimately it is maybe the feeding the multi-level inverter for the different kind of speed drive, but 12 pulse separate type diode with rectifier. Anyway, this one IA equal to, we can have this parallel connection also. It can fit one adjustable speed drive, it can fit another adjustable speed drive, but then there will be a problem because loading may differ and thus proper cancellations of this proper cancellation in primary site may not be feasible, but assuming that they are having a same kind of loading, you are required to balance somehow. Assuming that they have a same kind of loading, then you can also get cancelled your 5th and 7th, and ultimately you are left with the higher harmonic more than 5th and 7th, that is 11 and 13. So, you can have a same entity, but you do not connect them in series. So, this is a topology is separate type, 6 pulse converter rectifier fits a separate DC load, but there is only one risk involved. If the loading is different, then proper cancellation of the 5th and 7th not possible. Now, same way we can have, this is something that Siemens comes into the picture. You can Google or you can search the brochure of this Siemens drives, it is called Ruby drive, they have changed also the new nomenclatures. So, that was for the 24 pulse, but I have derived for the 12 pulse separate diode bridge rectifier type to simplify the structures of the system. So, you can see that this is a star, this is star, and thus you can have one, thus you can feed it to this converter. You can see that it goes from here, it goes to here, then there is another star. So, there is no phase shift, this one and this one, and ultimate, and then you feed it here, and thus you can have this voltage, and this voltage are connected in series, and here this one is your phase A, and or then what you have, this one is in same phase, but this one will have a 30° phase shifted. So, thus there will be a reflections of this drive spot here. Similarly, this is the star, ultimately you will feed it here. So, it takes this voltage from here, this star and this star will add up, and thereafter this voltage will be taking up a delta, and ultimately will feed here. Similarly, this voltage and this voltage will start off and we will have a feed there. So, in that way this 3 phase has been generated by cascading the 12 pulse, and ultimately it will cancel out the effective harmonic and it will give you a good quality drive, and this is generally the way of feeding a multi-level, these are all are cascade multi-level inverter topology. These are all the inverter block. This is one inverter block, one other inverter block. They have put them in series to build up the voltage. In that way, you can use them. This is called multiple cascade H bridge inverter fed drive. 24 versions has got the Siemens patent, and we just, for the sake of simplicity, I am showing the 12th version is of it, and it has huge advantage. See the advantages. Ultimately, you get a very good power factor in here as well as the THD. Apart from that, you are not using a special kind of transformer, because transformer, if you want to have a 18° phase shift, if you want a 20° phase shift, then you require to have a special constructions for it, and thus it requires a customizations in drives, and cost of, if you do the customizations, like if you take a shirt which does not commercially available, you require to pay more. Similarly, you require to have a special kind of transformer to be designed, and if you does not have a bulk demand, then cost will go up for those kind of entity, and commercial viability is a question mark then. But here you are not using any special kind of transformer, still you can achieve a very good THD. Students, I request you to simulate this circuit. It is very easy to simulate. It is and ultimately see that what kind of THD you are getting, and considering that this is an induction machine. So, comparisons with the so we can, but we can compare with this series type, these configurations, and generally what happen, we will observe that the DC current ripple will be little higher, and the line current THD will be close to this your series connected THD. So, this is the analysis of it for the 18 pulse converter for the separate rectifier. So, you can see that this gives you the, consider this B graph for the 18. So, here for the half load you have a THD close to 3%, otherwise it is same, actually this is the case we generally do not consider, because we will have some kind of leakage reactance as well as some kind of source reactance. So, this will be the case for the 0 source impedance. Thereafter, if you have 0.5 per unit, this is the B curve and the blue curve which can be referred into them, or this is comes into the picture most practical situations, and you can see that you can get little more than 3%. Same way, if you LS is equal to 0, then you can have 0.05% per unit and LS equal to 0.1 per unit, and in that way you can get LK equal to 0.05 per unit, and ultimately you can get A, B, C, all those curve, and this is for mind it till this point this current is in continuous conduction mode, but if you have a discontinuous conduction mode your power factor going to be high definitely, but THD also will be high for the for your displacement power factor. Now, 6 pulse converter for the inductive load, and this is something we have discussed, and these you can model as a current source, because L is very high, but practically speaking nothing is infinity, but when we say that L by R ratio is, let us say L by R ratio, if it is 10 times more than 10 millisecond and 100 millisecond, then we can take them, because the dropping will be so less, then we can consider that this entity is essentially a current source. And then what will happen? You will have a constant current source, and if you take this thyristors, what will happen? And ultimately you have, this is your load voltage for alpha equal to 0 for first basics, and this is the case for alpha equal to 30 degree, still you have a continuous conduction mode, and this is the alpha equal to 90 degree where you have a 0 load voltage, because you can see that positive area and the negative area are same, and thus you are essentially not taking any power from this grid side, and when you want to have a conversion, you want to send back power to the grid, that we are supposed to do the same thing in case of your PWM rectifier, then you will have this kind of waveform. It is same, just it is a mirrored image of 60 degree. Same way you can get the mirrored image of 8 for alpha equal to 30 degree, which not been drawn, and this is alpha equal to pi. In that case, this is the just mirrored image of this one with respect to x axis, and ultimately you get this figure, and that is quite common, you have studied in the power electronics courses. Now, what happen? You have a 12 pulse converter and you are feeding highly inductive load. Then what will happen, you will see that this is the this is for alpha equal to 30 degree phase shifted by the 30 degree both, and this is for alpha equal to 0, and ultimately in a voltage. So, they will be all have a phase shift. So, ripple will cancel out, and ultimately you get a, instead of a 6 pulse you get a 12 pulse in the primary volt, in the output voltage, and this will be the alpha equal to pi by 3, and this will be the output voltage pattern for highly inductive load. So, similarly, if you have if you put them in series, and with that will alpha equal to 30 degree, this is the simplified diagram, and ultimately you will get this current profile ISA and ISB. And thus, what you can expect, that in case of the highly inductive load for the 12 pulse converter, individual ISA 1 and ISA 2 will have, since it is a square wave waveform, will be reflected into the primary side. So, you can expect that THD will be as high as 30%, it is 28.73, and you will have the component of the 5th harmonic, 7th harmonic, 11th harmonic, 13th harmonic, and so on. But of course, you will find that it is a highly inductive load. Once you couple them for the 12 pulse, 5th and 7 will eliminate it, and ultimately you are left to 11 and 13, 23rd and 25th. So, generally you can see that if you add up the THD portion of it, you will get as high as THD of 31%, but if you want that THD, that should be around 15% for the 12 pulse converter. Same treatment what we do alpha equal to 0, you can find that THD is close to the 8 to 9% for 0 source inductance, but practical cases you will have for this be with the 5% source inductance, and that will be close to the 7%. And if you increase the alpha triggering angle, but you can see that THD generally increases. For alpha 60 degree, this is a case. So, thereafter alpha 40 degree, this is the case, and alpha 20 degree, this is the case, this is the drooping characteristics, and you get around 11% THD. For B alpha 40 degree, you get around 13% THD, and for alpha 60 degree you get around 13.5% THD. Same way power factor also almost even same in case of the A. So, it will be close to 1 and does not vary much, all those value is close to constant. Power factor, it comes some from the displacement power factor, almost that value is been continued. I shall continue with the 18 pulse converter from my from next class. Thank you for your attention.